I've been an FLL LEGO coach for about 10 years. This is my last year probably, with my second son graduating from FLL. So I thought I'd make a short video for beginning coaches to pass on some of the lessons I've learned the hard way. And this is not comprehensive, but this will really help you with your team as you help them build a working robot. So let me start with some fundamentals about robot design. This is typically called a box robot or a turtle robot. You can see it's square, and the design of the robot every year will be different based on the challenge. So for example, you see here, if there are a lot of obstacles that you have to get over, this is not the best design because it's pretty low to the ground. In some years, the competition will require that you have a very narrow robot or a very tall robot, but this is a good basic design. A few things about this. First of all, it's pretty stiff. It's more robots that are stiff tend to be a lot more reliable. Second, it's pretty heavy. It's a big, heavy robot that also improves reliability. The wheels are supported on both sides, and that's important because if you don't have them supported, they'll often bend, and that makes the performance unreliable. This type of wheel, I've seen the kids use lots of different kinds of wheels, and this tends to be one of the better ones because it can slide from side to side. Notice there's no tire on the front wheels. If you have tires on the front wheels, that makes it very difficult for the robot to turn from side to side consistently. Also notice that these wheels are doubled up. I'm not sure that's necessary, but the kids decided to do that because at least in the previous years they found that the traction has been better with two wheels, and this robot is pretty heavy, so I'm not sure it needs it, but that's what they did. And then this could have been narrower, but overall it's a very good design, solid, very stiff, like I said. This is the most common way of having drop-in attachments. You have the wheels, the motors side by side, and these turn like this, and they fit into these gears. See, they're doubled up. There are several ways to do that, but what the kids decided to do is double up on this and use these longer pegs. At least that's what they decided this year. And what this does is this pops right in, and when the wheels turn, it moves the handle in this case, and you can see here how the gears are designed. Here's a different attachment. You can see same connector here, and this goes up here, and it turns the wheel here. The third drop-in attachment looks like this. Drops in here, and it raises and lowers the arms. So really elegant design. You do need a lot of pieces. After 10 years we do have a lot of pieces, and that helps. Few other things. You'll see that the weight distribution is pretty even here, and this allows the robot to move straight. And what you will find is that changing the weight distribution of the robot, so if there's more weight on one wheel or the other, then that can really impact the traction on that wheel, and it makes the robot turn very differently. And you can see that for the most part, these attachments are symmetrical. The kids have learned through experience that having symmetrical attachments makes the robot the most consistent. One sort of last point is you want to avoid what I call axle contraptions, and those are attachments sort of like this. You'll see a lot of teams use axle attachments like this. They'll stick it on the robot, and they will it'll pick things up or operate something. And in general, these are not reliable for a couple of reasons. One is that it can move, and if it moves, it's often hard to tell if it's moved. Second is that I found in about 50% of the cases, the kids will drop the robot sometime during the season, during competition. But 1 out of 2. So once that happens, then the axle contraptions are much harder to put together. Which brings up a couple of other tips that I have. One is that you always want to take pictures of the robot after each practice, and certainly before competition, because when somebody drops that robot, and they certainly will, that's going to the pictures are going to really help. You should always have the kids carry the robot in a box, never carry it around by hand. That's a recipe for disaster. One reason why the drop-in attachments are so helpful is that if you have attachments that need to be pegged in or attached rather than just dropped in, you will use up a lot of time during competition. So typically, if you look at a competition, a lot of teams, out of the 2.5 minutes, the robot may be on the field for a minute or less. And a lot of the time is spent in base, adding different attachments, lining up the robot, and then selecting the program. So one thing I would recommend is to use master program, sometimes called a sequencer, and that's a program that has all your missions in a My block, and you select the mission. You just run a single program and keep it running, and you select the mission either by pressing one of these buttons. You can program these buttons to run a My block during the run of a program. So the master program is running, and you press a button that triggers one of the My block. Or you can use a touch sensor or a color sensor. It's all legal unless they change the rules. And that will save you at least 20 seconds, at least on the EV3 robots. On NXTs, it's not as critical because it's easier to change the programs, but that really helps. Second is to always use jigs to line up the robot. Unless your kids are good enough that they can program the robot to figure out where the robot is. So the best teams, what they do is they don't use jigs. They start the robot, and the robot figures out where it is as it goes over the lines or different landmarks on the field. If you can teach your kids about using drop-in attachments or attachments that are quick, and you teach them about master programs, that alone will save you at least a minute on the competition. Several things on the programming part. There are a few simple things that kids often forget when they are so excited to just start programming, or they never learn. One is the difference between using the brake versus non-brake at the end of the movement, brake versus coast. The other is understanding the difference between steer and tank. Another tip I have for you is that when you start, if you're using the gyro, and gyro is actually pretty good. When it first came out, the teams often didn't use it because it was unreliable, but what is really helpful when you use a gyro is to make sure the robot is absolutely still during when you turn it on. If it is not still, you introduce an error into the gyro, and gyro will basically um, not it'll basically drift, so it becomes unreliable. And the other thing is when you are using the program, when you're programming and you're debugging, it's generally helpful to have a Bluetooth connection or keep the robot connected to the computer, because then you can read all the sensors on the computer, and that's really helpful. You can also the other things that kids often don't know is you can run just part of a program from the computer. Not you don't have to run the entire program. You can run part of the program by using the run command that's inside the parentheses. And one really helpful way to debug is to put in sounds at different parts of the program, so you know where, for example, the program's getting hung up if the robot stops moving. So these are all the things that are basic, but if you're a beginning coach or a new team, you may not know. A few other things that you may not be obvious to you if you're just starting out. If your battery is really low or really high, then your motors will run differently, and the way that it runs at high versus low battery versus medium battery is different. Another is that if you build a robot so that the wires really bend hard, then it'll often result in the connections not being reliable, and your motors will run intermittently. So make sure you're not bending the wires severely when it comes out of the connections on the motors or the body. The other one thing to remember is there's always slop. There's the gears within the motor. There's slop, and within the connections, you know, if you have connections like this, obviously there's quite a bit of slop. So you need to know that there's going to be some inconsistencies introduced with that. Sometimes you can get rid of the slop. What some teams do is they will sort of make sure they pull the robot back a little bit, and that makes the slop consistent before each run. However, when you do that and you're using a master program, then you can introduce an error, which is that if a program is running and you move the motor manually, that will be detected by the sensor, and you will introduce error. So, for example, let's say the motor is like this, and you have it programmed to turn 90 degrees. It should turn 90 degrees like this. However, let's say the program is running, and you manually turn it like this, and then the program tells the motor to move 90 degrees. It's not going to move to here. It's going to move all the way here, because what happens is you've just changed the angle to -90 manually, and then when you say move 90 degrees, it goes to 0 and then to 90, so it'll turn 180 degrees. Very common error. Now let's talk a little bit about how to organize and run teams. Normally I recommend only about 5 to 6 kids per team. Beyond that, it becomes very hard to manage unless they're older. And what you usually want to do is you want to look at each year's mission and divide the mission or missions into let's say three runs, 3 chunks. So if you have 6 kids, you put 2 kids per robot if you have enough robots, and each team builds the same base robot but different attachments. And what they do is they do each of their missions, and then you combine the missions at least 2 to 3 weeks before the competition, because you want at least 1 week just for practice runs. You should make sure the kids look at the points that each mission is worth, there's always missions that have more points than others for less work every year. And you should also have the kids look at the rubrics, because the rubrics do change every year. And you should know that the way that the points are scored is that they usually rank each team on each one of the categories. So robot performance, or robot design, or core values. And it's sort of like golf. They add up your rank. So if you're second place in one part of the competition and 8th place in another, then that's 10 points. And the team that has the lowest points is the champion. So those are the sort of the organizational tips. It's also helpful to help the kids strategize every year, because every year there is something that makes the challenge difficult. Sometimes there are so many missions to do, you're going to run out of time. Other times it's very difficult to navigate because there are very few landmarks to navigate by. Sometimes there are restrictions that make it advisable to have a robot that's really tall or short or narrow or wide. So you can help the children sort of navigate through that as well. And finally, if you have kids that become more advanced, the best way to really operate the robot is not dead reckoning. Dead reckoning means you're going and programming the wheels to rotate a certain amount, but rather to use landmarks such as dark lines on the floor. So you can see on this robot, it's got a color sensor, ultrasonic sensor. It's got an ultrasonic sensor in the front, and actually ultrasonic sensors work reasonably well. And those can be used for the robot to figure out where it is. If you have a box robot, it can also square up against the walls, and that really helps you navigate. So in general, what you want to do is navigate using not dead reckoning, but landmarks and squaring up against the walls. Remember, when you square up, you want to have the motors coast, not brake at the end. And really advanced teams, the best way to ensure consistent missions is error correction. So for example, let's say your robot is supposed to lift something up. If you measure the rotation on the motors and you realize that it is getting stuck at a certain angle, then you know the robot must not be in the right place to do the mission, and you can have the robot move. Similarly, on the web you can find programs for stall detection. If the wheel stops moving, then the robot can sense that and make the appropriate changes. So these are the key tips I've learned over many years. I hope this will be helpful. These are all things that ideally you want to teach the kids in a hands-on manner. So rather than telling them, hey, don't make a robot that's too flexible, have them experiment and learn for themselves. Remember, the robot should be built 100% by the kids, not by the coaches. But what you want to do is guide them, because the robot season really isn't that long. And the first season, it took the kids almost the entire season to realize that having tires on 4 wheels made it just impossible to have consistent turns, right? Now that's the kind of thing that you can have them experiment with, and you might say, why don't you see if it works better without the wheels, and they can experiment and find out. So, ultimately, this is all about learning. Your job as a coach is to help them learn, and winning is great, but remember that this is all for fun. So have a lot of fun.